Around 14 billion years ago, everything we know, stars, galaxies, even the atoms in your body, burst from a point smaller than a dot. But what if the Big Bang wasn't the true beginning? Some scientists think it might have been caused by colliding dimensions, black holes hiding other realities, or quantum effects where time itself runs backward. What came before everything? Let's find out. Imagine typing divide by 0 into a calculator. It shows error. That's what happens when physicists try to explain the first instant of the Big Bang. They call it the singularity, where the universe shrinks to infinite density and heat. But infinite means our math has failed. Reality stops making sense. Even Einstein's theory of relativity can't describe such extreme conditions. At that moment, not only matter but space itself was being born. Before it, there wasn't even emptiness, just nothing. Temperatures reached 10 million trillion degrees, so hot that even atoms couldn't survive. Everything was pure energy. And here's the twist. If time began with the Big Bang, then asking what came before may not make sense at all, like asking what's north of the North Pole. That's why scientists suspect the universe never truly reached infinite density. Maybe the Big Bang wasn't a beginning, but a transition from something older we can't yet see. Clues are emerging in the cosmic microwave background, the faint glow left from the Big Bang. Tiny patterns within it suggest the universe might have had a story before its explosive birth. What once seemed like a dead end might actually be a doorway to something deeper. To uncover that mystery, we must zoom into the smallest scale of existence, where space itself unravels. Below 10 to the power of negative 35 meters, reality becomes chaotic, like boiling water. Physicists call this the quantum foam. Space isn't smooth, but constantly flickers with tiny bursts of energy. Here, pairs of particles appear and vanish in less than 10 to the power of negative 43 seconds. This isn't fiction. We've observed its effects through the Casimir experiment, where two metal plates are pushed together by invisible quantum pressure. Space is alive, endlessly creating and destroying energy. Now comes the astonishing part. This quantum foam may have existed before the Big Bang. It could be the eternal foundation of reality, bubbling with potential universes. Perhaps our cosmos was born from a single massive fluctuation in that sea, like a soap bubble expanding into infinity. At this level, time loses meaning. Past and future blur together, cause and effect collapse, and before the Big Bang becomes meaningless. Yet, something triggered the explosion we call cosmic inflation, a moment when the universe expanded faster than light. This solved many mysteries about our cosmos, but left one greater question. What set it all in motion? Maybe hidden beyond our Big Bang lies another phase of existence waiting to be discovered. Picture a balloon suddenly inflating, not slowly, but in a violent instant, leaping from marble-sized to basketball-sized faster than light could cross an atom. That's what cosmic inflation did to space itself. In just 10 superscript 3 seconds, a region smaller than a proton stretched to the size of a grapefruit. Space expanded so fast that nearby points were flung millions of miles apart, leaving behind only pure energy that would later cool into the first particles. To make this happen, the universe needed a special energy field, the inflaton field. It had to be balanced perfectly. Too weak, and inflation wouldn't start. Too strong, and it would never stop. Some theories suggest this balance was achieved through countless cycles of expansion and contraction before our Big Bang. Each cosmic cycle refined the conditions until inflation finally ignited. Think of it like a climber crossing several peaks before reaching the summit. Our Big Bang might just be the latest peak in a much longer cosmic journey. Simulations show these pre-inflation phases could have lasted unimaginably long, perhaps experimenting with different laws of physics and energy states. Traces of this earlier history may still exist. Gravitational waves from before inflation might still ripple through space, carrying whispers from a time before time. Scientists are building ultra-sensitive detectors to find them, a potential message from the universe's forgotten past. But inflation might not be the only way universes are born. Some physicists believe the Big Bang wasn't a beginning but a bounce, a rebound from a previous collapsing universe. Picture a cosmic heartbeat: expansion, contraction, collapse, and rebirth. Each cycle resets the cosmos like a vast washing machine, smoothing out imperfections and creating the near-perfect balance we see today. Evidence for this idea hides in the cosmic microwave background, the faint afterglow of the Big Bang. Its patterns are so uniform they almost seem too perfect for a single event, but in a cyclic universe, they make sense. Over trillions of years, each cycle irons out irregularities until the universe reaches a state of remarkable harmony. During contraction, time itself might reverse, events unfolding backward until the next bounce restarts the flow. Observations show our universe's expansion is now accelerating because of dark energy, but in the cyclic model, this won't last forever. Gravity will eventually overcome dark energy, beginning the next collapse. Each cosmic cycle could last around 1 trillion years. We're only 14 billion years into the current expansion, barely the opening act. Some scientists even think traces of earlier universes might survive the bounce, encoded in black holes or patterns of matter that pass through intact. One theory, the ekpyrotic model, suggests the Big Bang was caused by a collision of universes, two vast sheets of space-time, or branes, smashing together in a higher dimension. When they collided, the impact created our entire cosmos. Imagine two soap bubbles meeting. Ripples form across their surfaces, except here, those ripples became the matter and energy of our universe. This model explains why space is so smooth and flat. The collision's immense pressure evened out irregularities, like two rough boards pressed together until both sides become perfectly smooth. These branes float in a higher dimensional realm called the bulk, filled with countless universes like bubbles in champagne. Everything we know exists on the surface of one such brane. That collision, about 13.8 billion years ago, gave birth to our universe, but the branes themselves might be eternal, drifting through the bulk for eons before their next fateful encounter. Scientists believe they might one day detect proof of a cosmic collision by studying gravitational waves, ripples in space-time traveling at light speed. The impact of two colliding branes would have unleashed immense waves that could still echo through the universe today. Some versions of the ekpyrotic theory suggest these collisions aren't random. The branes are drawn together by forces in higher dimensions, crashing repeatedly to create new universes again and again. Each collision could form a universe with slightly different physical laws. Most would be empty and lifeless, but once in a while, conditions would align for stars, planets, and life to emerge. The other brane that collided with ours may still exist, drifting away through the higher dimensional bulk, perhaps carrying a parallel universe, a twin born in the same cosmic impact. To understand how that's possible, we turn to the strange math of extra dimensions and the idea that space itself might have a smallest possible size. According to loop quantum gravity, space isn't smooth or infinitely divisible. It's built from tiny loops, the fundamental threads of space-time. If you zoomed in far enough, space would look like a woven fabric made of microscopic loops, twisted together to form the illusion of continuity. This theory changes everything about what happened before the Big Bang. In loop quantum gravity, space can't shrink infinitely. As the universe contracts, these loops resist compression, like a spring that pushes back the harder you squeeze it. When space reaches its densest state, it rebounds, triggering a big bounce instead of a singularity. At peak compression, the universe's density would reach around 10 kilograms per cubic meter, a single teaspoon weighing more than all matter in today's universe. Yet, even at that unimaginable density, the loops prevent collapse. Simulations show that the bounce occurs smoothly, without infinities or breakdowns. The entire process happens in less than 10 superscript 3 seconds. If this model is true, the Big Bang wasn't the beginning. It was a rebound from a previous cosmic cycle. The evidence may still be visible in the cosmic microwave background, where scientists search for faint temperature patterns left by that ancient bounce. This idea also transforms how we view the future. The universe we live in is slowly dying, expanding, cooling, and dimming as stars exhaust their fuel. In about 100 trillion years, only black holes will remain. But according to the Big Bounce theory, death is only rebirth waiting to happen. As dark energy weakens over trillions of years, gravity will regain control. Expansion will stop and reverse, leading to a big crunch. Galaxies will collide, matter will heat to unimaginable temperatures, and the universe will shrink until quantum forces again resist total collapse. Space, compressed like a spring, will rebound violently, and a new Big Bang will be born. Each bounce may subtly rewrite the laws of physics. Most universes will remain sterile, but every so often, one will emerge with the right conditions for complexity, stars, and life. To us, it feels like a single cosmic story, but in truth, it may be one heartbeat in an eternal rhythm, the universe dying and being reborn forever. Scientists estimate that each cosmic cycle lasts around 2 trillion years. We're just 14 billion years into our current expansion, meaning almost 2 trillion years remain before the next great bounce. Yet, that bounce might already be happening beyond the dimensions we can see. Our universe may hide 6 extra dimensions, curled up so tightly that we can't detect them. According to string theory, everything, matter, energy, and space itself, is made of tiny vibrating strings that exist not in 3, but 9 spatial dimensions plus time. These strings are unimaginably small. If an atom were the size of our solar system, a single string would still be smaller than a tree. Think of a garden hose. From far away, it looks like a thin line, but up close it has width and depth. The hidden dimensions of string theory are curled up in a similar way, invisible, yet fundamental to reality's structure. Before the Big Bang, these extra dimensions might have been vast and open. The explosion may have caused 6 of them to curl up, leaving us trapped in our familiar 3-dimensional space. In that earlier era, matter and energy could have moved freely through all 9 dimensions, able to step out of our universe just as a person could step off a drawing on paper. The shape of these hidden dimensions determines everything: the kinds of particles that exist, the strength of forces, and the laws of physics themselves, much like how the shape of a violin defines its sound. As the extra dimensions curled up, the energy released could have powered the universe's rapid inflation, the moment it expanded faster than light. Mathematically, there are millions of ways to fold those 6 hidden dimensions, and each configuration could create a completely different universe. Most would be lifeless, no atoms, no stars, but one rare arrangement. Ours allows complexity in life. Some physicists believe that black hole collisions or cosmic transitions might briefly uncurl those hidden dimensions, giving us tiny glimpses beyond the limits of space. Scientists are even searching for signs of these dimensions, particles that vanish and reappear as if slipping through higher dimensional shortcuts. If proven, it would mean the Big Bang wasn't the beginning, but the moment our 3-dimensional world branched off from a much larger, unseen structure. And perhaps that structure never stopped creating. This brings us to the idea of eternal inflation, a cosmic factory endlessly producing new universes. Ours is just one bubble in an infinite ocean of ever-expanding space. While inflation ended long ago for our region, it continues elsewhere, spawning new universes in an endless process without beginning or end. Imagine a pot of boiling water, each bubble a new universe, each with its own Big Bang, its own galaxies, its own version of physics. The pot itself never runs out of energy or space. Everything we can observe, billions of galaxies across 93 billion light-years, is just one small patch inside one bubble. Beyond it lie countless others. If you could somehow escape our universe, you'd find yourself in the inflating space between bubbles, seeing entire universes scattered like glowing spheres in an infinite void. In this grand model, every possible universe exists, some with different gravity, different atoms, even different histories. There could be universes nearly identical to ours, except where you wore a different shirt today, or dinosaurs never went extinct. Collisions between these bubbles might even leave traces, faint scars in the cosmic microwave background, visible as strange hot and cold spots in the sky. Eternal inflation might also explain why our universe seems so perfectly tuned for life. In an infinite multiverse, every possible version of physics exists somewhere, and we happen to live in the one where life can arise. But that raises a haunting question. If every possible universe exists, what makes ours special? Are we just one random spark in an endless sea of reality, a fleeting thought in the mind of eternity? What if our entire universe exists inside a black hole? This isn't science fiction. It's a real theory that could solve some of the biggest mysteries about our origins. When a massive star collapses, it forms a black hole. But instead of creating a point of infinite density, the math suggests something extraordinary. It may generate a new region of space-time that rapidly expands, appearing as a universe from within. From outside, matter seems to vanish forever. But for someone falling in, space itself expands around them. What looks like death from one side could be a birth from the other. A black hole with the same mass as our observable universe would have an event horizon the same size as our cosmic horizon, hinting at a deep connection between black holes and the cosmos. If our universe exists inside a black hole, that black hole would belong to a larger parent universe, which itself could lie inside another, an infinite chain of nested realities. This model also explains cosmic inflation. The collapse that formed our parent universe's black hole might have triggered the rapid expansion we call the Big Bang. From inside, we see space inflating. From outside, it's just a star forming a black hole. As more matter falls into our parent black hole, it could feed energy into our universe, the mysterious dark energy driving our accelerating expansion. Simulations show that the interiors of rotating black holes can develop structures resembling galaxies and cosmic voids, just like what we observe. Every black hole, including the supermassive one at our galaxy's center, could contain its own internal universe with galaxies, stars, and possibly life. That means universes might give birth to other universes through black holes, a cosmic cycle of endless creation. But if we live inside a black hole, where does all the information go? Reality itself might be a hologram. Everything we perceive in 3 dimensions could actually be information encoded on a 2-dimensional surface. When matter falls into a black hole, the information isn't destroyed, it's stored on the event horizon. From our view, that 2-dimensional surface contains all the data about what fell in, just like a shadow on a wall holds the full outline of what's behind it. The holographic principle proposes that our entire universe works the same way. All the information about every galaxy, star, and person may be encoded on a 2-dimensional boundary at the edge of space. What we experience as depth and volume is a projection from that cosmic surface. In this model, the amount of information in a region depends not on its volume, but on its surface area. Doubling a sphere's size only quadruples its information. This may reveal what happened before the Big Bang. The Big Bang wasn't a beginning, but the moment when the holographic surface began projecting our 3-dimensional reality. Scientists are testing this by searching for signs of pixelation in space, tiny fluctuations that could expose the holographic grid. If space really is 2-dimensional, these cosmic pixels might soon be measurable. Even black holes themselves could be holographic storage systems, returning information through Hawking radiation as they evaporate. But how was this information encoded to begin with? The answer may lie in quantum tunneling, where universes can spontaneously appear from pure nothingness. At the quantum level, nothing is truly empty. Fluctuations constantly create virtual particles and energy bursts. And within this sea of probabilities, there's a tiny chance that a whole universe can tunnel into existence, a cosmic spark from absolute nothing. Such a universe would begin smaller than a proton, then inflate in an instant, becoming the vast cosmos we see today, filled with galaxies, stars, and life. Here's what makes this theory truly astonishing. A universe born from nothing would still have zero total energy. The positive energy of matter perfectly balances the negative pull of gravity, allowing existence to emerge without breaking the laws of physics. The odds of such an event are unimaginably small, about 1 in 10 carat, 10 to the power of 120. Yet in an eternal quantum vacuum, even the rarest possibilities eventually occur. Tiny, virtual universes could be forming and collapsing all the time, with only a few expanding into stable realities like ours. Recent experiments have observed quantum tunneling in systems of thousands of atoms, hinting that the same principle might apply on cosmic scales. Each tunneling event could create a universe with different laws of physics, numbers of dimensions, or types of forces. We exist in one where the balance happens to allow stars, planets, and life. If universes can emerge from nothing, there could be infinitely many, all coexisting in a vast multiverse. What we call before the Big Bang may simply be happening elsewhere right now. The multiverse isn't one theory, but a convergence of several: quantum mechanics, string theory, eternal inflation, all pointing toward the same idea. Reality is far larger than we can see. Imagine an endless cosmic ocean dotted with island universes. Each island has its own laws, its own history. Some are lifeless, others teem with possibility. In the quantum multiverse, every possible outcome of every event exists. Every choice, every path, every version of you. Inflationary physics suggests that new bubble universes constantly form within this infinite foam, each with its own Big Bang. String theory adds that the shape of hidden dimensions determines what kind of universe each bubble becomes. Some too unstable for atoms or stars to exist, others capable of creating life. In such an infinite structure, before and after lose meaning. The processes that created our universe could be unfolding right now in countless others. Some scientists even think subtle patterns in the cosmic microwave background may be collision scars from neighboring universes. If every possible universe exists, there are exact duplicates of ours scattered through the infinite foam, worlds almost identical, except for the smallest differences. It raises haunting questions. What makes this reality special? Are we just one version among endless variations? Yet the multiverse also carries hope. Even if our universe dies, others will continue to grow, evolve, and perhaps give rise to new forms of life and consciousness. Some physicists believe consciousness itself may be what lets us experience one specific branch of this infinite reality, that our awareness helps define which version of the cosmos becomes real. And perhaps the echoes of creation are still reaching us. Gravitational waves, ripples in space-time, carry information from the most violent moments in cosmic history. Colliding black holes and merging neutron stars create such waves, but the most ancient ones may predate our Big Bang entirely. These primordial gravitational waves are like fossils of the universe before time began. Detecting them could reveal whether our cosmos was born from a bounce, a brain collision, or a quantum fluctuation. They're faint, stretched, and weakened over 13.8 billion years. But scientists are building instruments precise enough to measure shifts smaller than 100,000th the width of a proton. Each pre-Big Bang theory predicts its own unique wave pattern. Finding them could finally show us what happened before the beginning. Recent discoveries have already confirmed gravitational waves from black hole and neutron star collisions. But these are relatively recent events in cosmic history. The real prize is detecting the primordial gravitational wave background, the faint echoes of whatever happened before our Big Bang. These waves could act like a cosmic barcode, carrying hidden information in their frequencies and polarization patterns. By decoding them, scientists might finally uncover which pre-Big Bang theory is true. Unlike light, gravitational waves pass through matter almost untouched, traveling billions of years without distortion, offering a clear view into an era too hot and dense for light to exist. Next-generation detectors, including massive space-based interferometers, are being designed to hear these ancient whispers, signals from before our universe was even born. But gravitational waves aren't our only fossils. The cosmic microwave background, CMB, the faint afterglow of the Big Bang, might also hold traces of earlier cosmic events. This ancient light, still glowing after 13.8 billion years, reveals tiny temperature variations showing how matter first spread through space. Yet hidden in those patterns could be clues from before the Big Bang, faint fingerprints of a previous universe. Think of the CMB like ripples on a lake. Most are caused by present winds, but some might trace back to older disturbances deep below the surface. Similarly, the CMB may carry the imprints of events that predate our cosmic beginning. Different pre-Big Bang theories predict unique patterns. Cyclic universes might leave repeating temperature correlations, while colliding brains could create geometric, crop circle shapes in the radiation. Detailed CMB maps have revealed strange anomalies, alignments and asymmetries that don't fully match standard Big Bang predictions. One striking clue is the discovery of non-Gaussianity, patterns too organized to be random, possibly caused by pre-existing structures shaping our early cosmos. Polarization data also hints that gravitational waves were present during inflation, and their exact characteristics may reveal if they came from inflation itself or something before it. Even more fascinating, the CMB might show evidence of multiple universe cycles. If our Big Bang was a bounce from an older universe, its light could carry recycled signatures from that past epoch. Advanced simulations now help scientists predict what each pre-Big Bang scenario should look like, bringing us closer to decoding our true origins. But to truly understand these cosmic fossils, we must confront one of the greatest mysteries of all: dark energy. It makes up nearly 70% of the universe, yet remains invisible and unexplained. All we know is that it's pushing galaxies apart faster and faster. What's puzzling is how perfectly its energy matches the idea that our Big Bang came from a larger cosmic structure, as if dark energy is the lingering footprint of whatever birthed our universe. Imagine it as the foam on a poured drink, not the drink itself, but the byproduct of its creation. In some theories, dark energy naturally arises from the same processes that triggered our universe, brain collisions or cosmic bounces, leaving behind energy fields that continue to expand space. Its value seems finely tuned, too strong, and galaxies could never form, too weak, and the universe would have collapsed. That perfect balance suggests it might be part of the selection process that shaped our particular reality. Observations show that dark energy only became dominant in recent cosmic history, just as life began to emerge. Some believe it isn't constant at all, but slowly evolving with time, perhaps linked to the rise of complexity and consciousness. Simulations predict very different futures depending on which theory is true: a big rip, a gentle fade, or another cosmic bounce. If dark energy is a relic from before time began, studying its evolution could finally reveal what sparked the Big Bang. Upcoming space telescopes aim to measure it with unmatched precision, searching for patterns that point back to our origins. Yet the deeper we explore, the more profound the question becomes: what does before even mean when time itself didn't yet exist? Our minds are wired to think in cause and effect, past and future. But if time began at the Big Bang, there was no before. Still, some timeless condition, must have triggered creation itself. How can a cause exist without time for it to unfold? It's a mystery that sits at the edge of physics and philosophy, the moment when not just matter and space, but time itself came into being. Imagine asking what's north of the North Pole. The question seems logical until you realize north only has meaning within Earth's coordinates. Beyond that, the concept itself breaks down. In the same way, before only exists within the framework of time. Quantum mechanics, however, blurs this boundary. In the quantum realm, cause and effect aren't always clear. Events can happen without defined causes, and particles can briefly exist and vanish without violating physics. Some theories suggest that time itself emerged from a deeper, pretemporal reality where causality works differently. The Big Bang may have been the moment when timeless quantum connections solidified into the familiar flow of past, present, and future. Loop quantum gravity proposes that time isn't smooth but made of tiny, discrete moments, like frames of a film. At the Planck scale, the flow of time breaks into quantum jumps, and the Big Bang could mark the shift from this flickering quantum reality to continuous time. String theory adds another twist. Time may not be fundamental at all, but an effective motion through higher dimensions. And the holographic principle goes even further, suggesting that time and reality themselves are projections of information encoded on a two-dimensional cosmic boundary. If so, asking what happened before the Big Bang may be meaningless, because time is simply a way of processing that information. But this raises a deeper puzzle. Where did all that information come from? Information, unlike matter or energy, can't be created or destroyed. It can only change form. Every particle, atom, and star encodes information about its structure and history. If the Big Bang truly created everything from nothing, it would violate this rule. That means our universe's information must have existed in some form before the Big Bang. Think of information like water. It can freeze, evaporate, or condense, but the total amount never changes. Likewise, information can shift between matter, energy, or quantum states, yet the total remains constant. The holographic model offers a stunning answer. Our three-dimensional universe might be a projection of data stored on a cosmic boundary. The Big Bang wasn't the creation of new information, it was the activation of that projection. All the blueprints for galaxies, stars, and life could have been encoded there long before space and time began. Black holes support this idea. When matter falls into one, its information isn't lost. It's stored on the event horizon. If our entire cosmos exists within a higher dimensional black hole, our universe's information could be encoded on its surface in a parent universe. Quantum mechanics deepens the mystery further. In the many-worlds view, every quantum decision creates branching realities, meaning our universe might be one outcome in a vast quantum tree extending beyond the Big Bang. The cyclic model adds that information gets recycled through endless cosmic bounces, reorganizing each time a universe collapses and rebirths. Recent quantum information research even suggests that information is more fundamental than space or time, and reality itself might emerge from information processing. If true, universes could be interconnected by vast webs of quantum entanglement, linking particles across different realities. Entanglement is already strange within one universe. Two particles can instantly affect each other, no matter how far apart. But if entanglement extends across the multiverse, particles in our world could be connected to those in parallel universes, forming an invisible quantum network spanning reality itself. Imagine two magical coins that always land opposite. Flip one here, and the other changes instantly, even across universes. These connections might explain why our universe's physical constants seem perfectly tuned for life. Perhaps they're not random at all, but balanced by correlations with other universes through a grand entangled structure. If our universe emerged from a prior cycle or brane collision, its particles might still carry entanglement from that earlier epoch. Information about what came before the Big Bang could still echo through quantum links. bridging realities long gone, yet still intertwined in the fabric of existence. Scientists believe we might someday detect signs of cross-universe entanglement by spotting tiny violations of quantum rules that ordinary physics can't explain. If particles in our universe are entangled with others in parallel realities, those links could leave measurable traces. Modern experiments are already stretching what's possible. Researchers have entangled hundreds of particles and even sent entangled photons thousands of miles apart. The next leap could be detecting connections that reach beyond our universe. If such entanglement exists, it could reveal information about other realities, even about what came before the Big Bang. It might offer a way for information to pass across space, time, and perhaps between universes. But this also raises a deeper mystery. If quantum states span multiple realities, what decides which version of reality we actually experience? Some physicists think the answer lies in the link between consciousness and quantum mechanics. What if consciousness doesn't just observe reality, but helps choose it? In quantum physics, particles remain in multiple states until observed. The famous double-slit experiment proves this. A photon travels through two paths at once, yet collapses into one when measured. No one fully understands what triggers this collapse. Some say it's a property of nature, others that it's caused by the environment. But a growing view suggests consciousness itself could be the deciding factor. If true, consciousness may have shaped the universe's very history, collapsing countless possible timelines into the one we experience. Before life emerged, the cosmos might have existed in a superposition of many histories. Conscious beings could have selected one specific version. Imagine it like a cosmic choose-your-own-adventure story. All outcomes exist until someone reads the page. The act of observation decides which story becomes real. This idea connects to the mystery of fine-tuning. Our universe seems perfectly designed for life and awareness, maybe not by chance, but because consciousness selected the conditions that allowed it to exist. In the many worlds interpretation, all possibilities exist in parallel, but consciousness experiences just one branch. In that sense, other versions of you might live in universes with different laws and histories. Recent research in quantum biology hints that consciousness itself might use quantum effects in the brain's microtubules, in photosynthesis, even in memory. If consciousness has quantum properties, it might access information from alternate realities. Intuition, creativity, or déjà vu could be faint echoes from other timelines. Some scientists go further. Maybe consciousness is not a product of matter, but a fundamental force like gravity or electromagnetism, woven into space-time itself. If so, consciousness existed before the Big Bang, and our awareness is the universe becoming aware of itself. From here, the idea turns even more radical. Perhaps reality isn't made of matter at all, but of mathematics. In this view, everything, particles, forces, even consciousness, is part of a vast mathematical structure computing itself into existence. Just as characters in a video game believe their world is physical, our reality might be a mathematical simulation following logical rules. This mathematical universe explains why math describes the cosmos so perfectly, because reality is mathematics. The Big Bang, then, wasn't a physical explosion, but the moment one mathematical structure began calculating itself into being. Like the number pi, which holds infinite truths without existing in space or time, our universe may exist as a self-running equation. Supercomputer simulations show that simple mathematical laws can produce complex cosmic patterns, galaxies, clusters, and voids, just like ours. If every mathematical structure defines a possible universe, then countless realities exist, though only a few support conscious life. Consciousness itself could be a mathematical process, our brain's biological computers running cosmic algorithms. The beauty we see in math and nature might be recognition, mathematics seeing itself. In that sense, what existed before the Big Bang wasn't matter, but pure logic. The universe began when one consistent mathematical rule set came alive, computing everything we now call physical reality. Some physicists believe our universe may not be truly stable. It could be living in a false vacuum, a temporary energy state that only seems permanent. In particle physics, even empty space is filled with quantum fields. These fields have energy levels, and our universe might sit in a local minimum rather than the true lowest point. Imagine a ball resting in a small dip on a hillside. It appears stable, but a small push could send it rolling into a deeper valley. Likewise, a quantum fluctuation could trigger vacuum decay, creating a bubble of true vacuum that expands at light speed, rewriting physics as it goes. Inside such a bubble, atoms and forces as we know them could not exist. If that sounds terrifying, there's comfort in knowing the odds are astronomically low. The universe will likely last trillions of years before such an event. But this concept might reveal what came before the Big Bang. Our universe could itself be a bubble formed from vacuum decay in a larger, older cosmos. The discovery of the Higgs boson hints at this possibility. Its mass places our universe right on the edge between stability and collapse. Some scientists even propose that vacuum decay is how new universes are born. Each bubble becomes a self-contained cosmos, expanding with its own Big Bang and unique physical laws. This process could be happening constantly throughout an infinite multiverse, a cosmic foam filled with bubbles of reality. And if consciousness can influence quantum events, advanced beings might one day learn to trigger such transitions intentionally, creating new universes by design. But vacuum decay may be only one form of cosmic reproduction. A bold theory called cosmic natural selection suggests universes evolve like living organisms. When black holes form, they might create new universes on the other side of their event horizons. Each child universe inherits slightly altered physical constants from its parent. Universes that produce many black holes create more offspring, while sterile ones fade away. Over countless generations, the multiverse would become dominated by universes optimized for black hole formation, which might explain why our own universe seems fine-tuned for stars, the birthplaces of black holes. If this cosmic evolution is real, our universe's physical constants should maximize black hole creation, and evidence suggests they might. Gravity's strength, particle masses, and cosmic expansion rates appear precisely balanced for that outcome. Yet the process could be far more complex. If consciousness affects quantum mechanics, then intelligent life could influence how universes reproduce. Advanced civilizations might learn to create new universes, passing on their knowledge, even their values, to cosmic descendants. This could explain why our universe seems finely tuned for complexity and awareness. Conscious universes would naturally be more likely to give rise to intelligent creators, while lifeless ones would end in extinction. Over unimaginable timescales, perhaps spanning billions of cosmic generations, universes could evolve, reproduce, and compete in a vast cosmic ecosystem. And then comes the most radical idea of all. What if our entire universe is not natural at all, but a simulation? As computing power grows, we're already simulating miniature universes. A civilization far more advanced than ours could easily simulate whole cosmoses, complete with conscious beings unaware they're digital. To such beings, their reality would feel just as real as ours does. Just as video game worlds become more lifelike with each generation, future technology could create conscious simulations indistinguishable from real universes. The Big Bang might have been the moment someone pressed start. What we see when we look into deep space could be rendered on demand, calculated only when observed, like graphics loading in a game. If that's true, the real question isn't what came before the Big Bang, but who started the simulation and why. Were they scientists studying their own origins, beings preserving ancient consciousness, or simply creators exploring what it means to exist? If reality is a simulation, scientists might one day detect its limits. Advanced physics experiments could uncover tiny computational glitches, pixelation at extreme energies, or subtle rounding errors that hint our universe runs on finite processing power. This idea also explains why our cosmos seems perfectly tuned for life and awareness. A simulated world would be designed for complexity, not emptiness. And if simulated beings eventually learn to create their own simulations, reality could exist within an infinite hierarchy, worlds within worlds, each unaware of the creators above them. In that case, asking what came before the Big Bang becomes a question about who programmed it and why. Yet these theories are not pure imagination. They make predictions we can test. Science thrives on falsifiable ideas, and even the most exotic pre-Big Bang models point to measurable evidence in our universe today. Gravitational wave detectors, such as LIGO and Virgo, already capture cosmic collisions. Future observatories could detect the faint hum of primordial waves, echoes from before time as we know it. Different theories predict distinct signatures. Bouncing universes, colliding brains, or quantum tunneling each leave their own imprint on space-time. The cosmic microwave background, that ancient afterglow of creation, is another key. Satellites like Planck have mapped it in extraordinary detail, but upcoming missions will probe its polarization patterns even deeper. Subtle irregularities, too organized to be random, could reveal traces of structure that existed before the Big Bang. Particle accelerators, such as the Large Hadron Collider, are also probing deeper into reality's foundation. Discoveries there could expose hidden dimensions, vacuum instability, or clues that our cosmos is part of a grander multiverse. Meanwhile, telescopes like James Webb are peering farther back in time, seeing galaxies that formed soon after the Big Bang. Their light may hold information about what came before ordinary cosmic evolution began. Even quantum experiments might offer evidence. Entanglement tests could uncover non-local connections beyond our universe, or computational limits hinting at a simulated foundation. The most thrilling possibility is convergence, multiple lines of evidence all pointing toward the same origin. Whether the data favors a cyclic universe, quantum birth, holographic projection, or simulation, the implications are staggering. Humanity would no longer see itself as a cosmic accident, but as part of an infinite story. If reality is cyclical, then we are not at the beginning of everything, just one chapter in an eternal sequence of birth, death, and rebirth. If our cosmos emerged from a higher dimensional collision, we are the living remnants of a vast event that happened in realms beyond imagination. If black holes birth new universes, then every black hole we observe could contain entire galaxies and civilizations of its own. And if the universe is a holographic projection, then what we call reality is simply information woven into patterns of consciousness, a grand act of cosmic computation. In that sense, we are not just observers, but participants, helping the universe create and refine itself. Perhaps consciousness itself shapes which version of reality we inhabit. In a multiverse filled with infinite possibilities, awareness might be the mechanism that chooses one timeline from countless options. Future civilizations may even learn to communicate across universes or create new ones entirely, becoming architects in the ongoing evolution of existence. Even if we never reach that stage, the realization itself is transformative. We are not mere byproducts of chaos, but expressions of the universe awakening to its own creative power. The Big Bang was not the ultimate beginning. It was a transition. And consciousness, yours, mine, ours, is the universe's way of continuing the story, one moment of awareness at a time.